ops lectures, you've learned that it's a solution to the Yang-Baxter equation. So this is the equation we'll be interested in solving. For our purposes, it'll really be sufficient to take a single vector space over a field. Okay? And what's an R matrix? An R matrix is going to be, we'll have a dependence on some spectral parameter, like showed up in the end of Eddinghoff's lectures yesterday. And this will be some rational valued matrix acting in the tensor square of this vector space. And what's the quantum Yang-Baxter equation? Well, it's just the Reiter-Meister 3 equation. It's an equation for the braiding of representations of some quantum group. It tells us that we can apply 3 different operators cooked out of this R matrix in 2 different ways. First, we can apply them in this order, or we can apply them in the reverse order. And these are supposed to be equal operators. And so where do these operators live? They act on the triple tensor product of this vector space over the field of rational function in these variables, u1, u2, u3. Okay. And this is a pretty complicated equation, right? If V is finite dimensional, say of dimension n, then there are n to the 6th equations and n to the 4th variables. So the fact that you have a solution to it, it indicates that something pretty special is going on. And indeed, as we've heard a little bit about from Eddinghoff, and we'll probably hear more from either Eddinghoff or Andre, once you have a solution to this, in other words, once you have some braiding on a tensor category, you know it has to be the representation category of some quantum group. And so once you have a solution, you can produce a quantum group for which V and its tensor powers are representations. So this is the kind of one key ingredient from which one can construct a quantum group action. So one can do this abstractly, a la Eddinghoff. One can do this very explicitly, which Andre might explain, maybe. So this is a good thing to have a solution to, hopefully. And so one kind of question people are getting at this week is how to use geometry to find solutions to this. So this is the equation we want to solve. And solutions are going to come geometrically. And so this vector space will be the cohomology of some variety. And Devesh Malik and Andre have 2 different ways to do this. And the first is that V will be the cohomology of some Nakajima variety, which I'll call x1. And so let me draw the quiver to which this variety x1 could correspond. I could have whatever's going on anywhere else, and I just want one framing node at which I put dimension 1. And how does R arise? So R will act on and so maybe this is equivariant with respect to some large torus action. And R will act in the tensor square of V. And how do I get this R? Well, as we've seen, this x1 sits as the part of the locus of fixed points of some larger Nakajima variety if you've been doing the exercises. That is, I can take the same quiver, but just replace this one with a 2. So these are supposed to be isomorphic blobs. And here, I have some torus acting, or some GL2 that acts on this framing. And the fixed locus with respect to this GL2 is by one of the exercises the product of x1 with itself. And maybe Andre will also explain this, but after suitably localizing, he'll explain 2 ways to map from the tensor square of this cohomology, that is the cohomology of this right-hand side of the fixed locus, to the cohomology of this whole larger space, x2. Yeah? Sure, yeah. So maybe this should be maybe this should be I should take some torus A inside GL2. Yeah. No, there shouldn't be a difference. It's okay? Yeah. Yeah, no, you want just the torus. Thanks. And these maps will depend on some co-character of this torus, or really some kind of chamber in which this co-character lies, and there'll be 2 of them. And they'll be called the stable envelope maps. And this R matrix will be one of these stable envelopes composed with the inverse of the other. So these depend, yeah. So these will depend on some choice of a co-character of A. And then from the properties of these maps applied to some kind of larger diagram where I replace x2 by x3, one gets the Yang-Baxter equation kind of from formal properties of these stable envelope maps. And so I think this is what is coming, maybe? Hopefully, OK. So this is kind of method 1. So this works for next part.
There's no additional information. Well, I guess the partial lecture could be some additional information. There's nothing else I have to explain.
For Nikita. OK. And so I want to talk about Hilbert schemes of points on surfaces. And from one of the exercises, you've learned that that's an example of a Nakajima variety that looks like this. All right, so if I take the Hilbert scheme of points on C2, what U is. Yeah, so this U here is so U is some element in equivariant cohomology, in A equivariant cohomology of a point. So if this A is maybe e to the U1, e to the U2, then this U is the difference in the weights of this torus. And so these kind of rational function fields come after you invert the characters of this torus. So if I take this particular Nakajima variety, writing this with a K, which will certainly trip me up. This is supposed to be equal to the Hilbert scheme of K points in C2. And so what is this Hilbert scheme? No one's written down a definition of it. So for those who haven't seen it before, what is the Hilbert scheme of K points on an arbitrary surface, S? This is some scheme that parametrizes zero-dimensional length K subschemes of S. So I take subschemes of S that are to dimension 0 and of length K. And this is some variety that can be thought of as parameterizing configurations of K points on S. So for example, if I just have the Hilbert scheme of 1 point on a surface, there's not so much interesting that can happen. I just get the surface back itself. But already, so maybe I'll denote this S upper brackets K to save me writing Hilb. And if I take the Hilbert scheme of 2 points on S, already some interesting things can happen. Is it OK if I write down here? Let me know if you can't see. This will be the union of two different types of configurations of points. First, if the points are different, there's not much interesting scheme structure I can put. I just have the direct sum of the sheaves supported at these points. But when my points coincide, then something interesting can happen. So for example, if I take C2 and I look at the sublocus of schemes supported at the origin, and I look at sections of O of Z, well, I have to have 1 as a section, and I have some AX plus BY where so maybe these are my coordinates, X, Y, and C2, and A and B are complex numbers. And I can rescale this A and B. And so I have two numbers, C2 up to some scaling C. And so what I see are that there are a P1 worth of schemes supported at this origin. In other words, this scheme not only remembers the point, it remembers the direction along which the 2 points coincided, along which they collided. So here, and at P equals Q, I have a P1's worth of points. That I definitely can't write down there. And so what's my conclusion? It's that the Hilbert scheme of 2 points is obtained by blowing up the product of the surface along the diagonal and then quotienting by the permutation that swaps these two factors. Okay. And so this kind of first solution to the Yang, the first kind of construction of this R matrix will come later. What I want to focus on today is a second construction, And this construction works for arbitrary S, or essentially any S. So the second construction will start with the Hilbert scheme of S, and we'll let V be the cohomology, possibly equivariant of Hilbert S. And we'll use the kind of representation theory of this Hilbert scheme to construct the same solution to the R matrix you get when S is C2, and you get some new solution when Hilbert of S is not a Nakajima variety. And so how will this construction go? So we'll produce an R matrix using a Virasoro algebra action. On the cohomology of the Hilbert scheme. And I should say that when I mean cohomology of the Hilbert scheme, I want to take the union over all k of the Hilbert scheme of k points. So these representation theoretic structures only emerge when you group Hilbert schemes of all number of points together. All right. Sorry? It's just a union, so disjoint union. Yeah, there's no kind of gluing. Yeah. And so when S is equal to C2, Malik and Akunkov showed that you recover the same R matrix as 1. And for general S, you get something new. You get a new solution to the Yang-Baxter equation. Okay. Any questions so far? Why S isn't C? Why don't we consider C? Well, so the Hilbert scheme of points on C is just the symmetric product. I mean, in principle, one can try to construct R matrices acting there, but then it's just well, but neither are these, right? These are Nakajima varieties for general S. I mean, in some slight way, this construction, when S is T star Grassmannian, can be related to the nth symmetric power of P1 is Pn, and so this is kind of sitting somewhere in this Grassmannian story if you wrap your head around it enough. But somehow this is kind of a more interesting variety, I guess, than the Hilbert scheme of points on C. Okay, so let me review or explain the representation theory associated to this. So for this construction to work, we can't quite consider general S. So there's some kind of mild assumption on S I want to put. S will either be, so S is going to be a smooth quasi-projective surface. Over the complex numbers. And it should either be proper or kind of equivariantly proper. In other words, there's some action of a torus on the surface whose fixed locus is proper. So I guess if you allow trivial tori, the first case is a subcase of the second. And why is this good? Well, it allows us to integrate over S. So we have some notion of integration, either just ordinary integration or using equivariant localization, as was explained to us yesterday and today. So in other words, this cohomology ring has the structure of a Frobenius algebra. So Sasha Braverman explained what this was last week. These will differ only slightly from the kinds of Frobenius algebras that showed up in studying TQFT in that the surface might have odd cohomology. So this is a potentially kind of, it's a graded commutative Frobenius algebra instead of a commutative Frobenius algebra. And the pairing is just integration. So to give you a Frobenius algebra, I need to tell you what a pairing is. And I'll just multiply those classes, and it's convenient to have this negative sign floating around. Yeah, so this isn't too important, but I say it in part to make connections with what some people saw last week. Okay. And as Andrea explained this morning, one way to get interesting actions of algebras on varieties is to find correspondences. And the Hilbert schema of points is a particularly rich source of correspondences. And so what do we need if we want to go from the cohomology of one Hilbert scheme to another? We need some correspondence between them. And so if I have, say, a Hilbert scheme of, let's say, k points and a Hilbert scheme of k plus n points, I'm going to define some subclass and it'll be indexed by a cohomology class of my surface. And this will consist of pairs of subschemes. One sitting inside the other. And the condition is that we want these two subschemes to differ only by a fat point supported along this class gamma. In other words, the support of the quotient counted with multiplicity is going to be n times the point, n times some point p, and p should lie on the class corresponding to gamma. So maybe I'll draw a picture of some sample element. Here's my surface S. Here's some subscheme, so maybe there's some isolated points, and there's a really thick point. And here's my class gamma. And then another subscheme could be the following. So gamma could be in H2, it could be in H4, it could be, yeah.
Why is it a class and not actually a cycle? Like, what does it mean?
Cycle, yeah, I should say cycle. Equivariant cycle. Yeah. I mean, somehow, if you multiply gamma by 2, you want to keep track of that in some sense. So that's why I said class. So maybe the more rigorous way to do this would be think of this as some correspondence sitting over all of S, and then you'll pull back the corresponding cohomology class from S. Let me repeat what I'm about to. I'll say what I'm about to say after I describe the correspondence. So yeah, I guess I sacrificed that detail for the sake of exposition, but maybe it's confusing. So this y gamma gives us some correspondence that I'll call alpha minus n gamma, and this will go from. Forgive me, I'm going to drop all equivariance. So just assume all cohomology is equivariant, if need be. And this will go from the cohomology of this Hilbert scheme to the cohomology of this Hilbert scheme. And how will this operator look? Well, Andre described how these look in K-theory, but one can do the same construction in cohomology. This comes equipped with 2 projections, 1 to each factor. And this operator is just equal to pull back along this first map composed with push forward along the second map, P2. In other words, one can think of it as adding a point of thickness n along the cycle gamma. Again, if one wanted to do this really rigorously, one could erase this gamma, include an s down here, and then if I wanted gamma, I would pull back this class along s and take the cut product before pushing forward. But let me not worry about that for now. Any more questions about this? OK. And then similarly, so these are what are called creation operators. They add points.
Can you say again where gamma is?
Gamma is a cohomology class of the surface. Any cohomology class, yeah. Yeah, yeah. And then up to cohomology, they'll give you the same operator.
Also, there's no restriction. This restriction just factors through the support of Z2 minus Z1. You don't care about like what direction Z2 minus Z1 is.
No.
Points normal to gamma or something.
Exactly, exactly. Yeah, yeah. So that's in adding this point kind of encodes all the complications of what can happen when I add a thick point at gamma. So the larger n is, the more kind of complicated the thing I could be adding is. Okay, so I've given these correspondences going one way, these creation operators that by convention come with this minus n, and then I can define their counterparts. So this is, I suppose I should specify that n is positive here, and if I wanted to define their counterparts, it's just given by the same correspondence in reverse, and because of this choice of sign I've put here, it'll be convenient to include this choice of sign. So this is some sign times the same correspondence transposed. So I have this family of operators corresponding to adding thick points, removing thick points, and it's a theorem that's separately attributed to Granovsky and Nakajima, that these resulting operators form a version of the Heisenberg algebra labeled with values in the cohomology of my surface. So if I take the commutator or supercommutator, rather, of these, of alpha m gamma and alpha n gamma prime, these will be equal to 0 unless m plus n equals 0. But if n is negative m, then I get some factor times the intensity. Sorry? No. No. It's really a Heisenberg algebra, yeah. Okay. And so yeah. The bracket gives you some number, or more precisely, a polynomial. So I guess a rational function. So some element in, certainly that will lie within the fraction field of equivariant cohomology of a point. So if I have a proper surface, I really get some number. And if I have something like C2, then in principle, it could have some kind of denominator that's introduced when I do this equivariant localization. But you can just think of it as a scalar. Yes. Yeah. If my, yeah. Okay. I'm going more slowly than I had hoped, but that's okay. So under this algebra, we have some algebra that acts on this, and one can ask, what does this module look like? So maybe I'll call this module Vs. It's the same V as before, only I've labeled it with the surface. And this is a lowest weight representation for, or also known in the context of Heisenberg algebras is for Fock space for this Heisenberg algebra. So for example, if I let the vacuum vector be the cohomology of the Hilbert scheme of 0 points, which is just a point, then all of these annihilation operators really annihilate the vacuum. And acting with the creation operators, I can produce a basis. So let me just tell you how this looks when S is equal to C2. A basis, I don't have many interesting cohomology classes. Up to a scalar, the only cohomology class is the unit. And so we don't have to worry too much about this gamma. And so a basis over this field that was asked about earlier is just given by partitions. It's just given by applying these creation operators where I read off the index from some partition. Take the product over I. Of alpha minus lambda I applied to the vacuum, and here lambda ranges over all partitions. And so we have our Heisenberg action. So maybe I should write the word, Heisenberg on the board. And so it's kind of this is some kind of infinite dimensional Lie algebra, but it's finitely generated, and it's kind of remarkable that from this we'll produce an R matrix that in turn implies the existence of some much larger, much more infinite dimensional, infinitely generated algebra that will act on this cohomology. And so that'll be produced via the R matrix, and I mentioned that we'll get that R matrix from a Virasoro algebra. And so in general, anytime you have a Heisenberg algebra, the Fagan-Fuchs construction tells us how to produce the action of a Virasoro. And so how does that look? Well, one can write this down kind of purely algebraically. And so to do this, first let me introduce another formal parameter, kappa. And this Virasoro algebra will again take a number n, we'll take a cohomology class of my surface, and it'll be a function of this formal parameter kappa. And it'll be some quadratic expression in my Heisenberg generators. And it'll look a lot like the usual Virasoro algebra you may have seen in infinite dimensional Lie algebras before. Maybe I'll write it like so. So I'll write the formula and then I'll explain the notation. So the first thing is what are this gamma I and gamma I double prime? This is something we've seen before in Pavel's lectures. This is just, I guess without the indices, it would be a Sweedler notation. So So I mentioned that the cohomology of a surface is a Frobenius algebra. In particular, that means it comes with a coproduct. And so I take my class gamma, I hit it with the coproduct, and I can write it as a sum of tensor factors. And that's where I get my gamma I and gamma I double prime. So I guess I've suppressed the sum over I. Here, this double brackets refers to normal ordering. And so this just means I take all of the annihilation operators, and so these with positive n, and I move them to the right. So this is and so that's how these are obtained algebraically. I should say there's a way to obtain them geometrically. And roughly speaking, one takes these operators and commutes them with intersection of the boundary of the Hilbert scheme. Or another way to think about this is the first Chern class of these tautological bundles that you've studied on the exercises. So if I commute these with multiplication by first Chern classes of tautological bundles, these Virasoro are sitting inside the result of that computation. So yeah, let's write down the Virasoro relation, and then you'll see. Yeah. So it depends. This class I constructed depends on gamma. You can think of it as we want to add a fat point along the cycle gamma. Yes. Yeah. I should not have said this. So really, the kind of proper way to define them is I take the same incidence correspondence, and I think of it as sitting inside. What did I say? I said.
So this space is you only require one of the functions to be at one point.
Exactly. Yeah. Yeah, and then really this if I want to take the operator, so what did I do before? I had so now if I want to really properly encode the dependence of gamma, what I want to do is pull back along SK. I want to pull back gamma along S and then push forward along P3. And so from this kind of description, one sees the dependence on gamma more clearly.
And also, is there any relation between, let's say, alpha 2 and then alpha 1 squared?
So those will commute by this relation. Yeah. Yeah. And so just like before, where we got some Heisenberg algebra with the kind of usual Heisenberg relations decorated by cohomology classes of the surface, now we will get Virasoro relations also decorated with cohomology classes of the surface. So one has the following proposition. If I commute two of these Virasoro classes, what I get what looks like the usual Virasoro relation, decorated with the cohomology class, and then again, I have this extra term that should look familiar to those who've seen the Virasoro algebra before. I have some term that depends on m plus n, and then I have some more complicated expression that will incorporate the cohomology classes from my surface. And so to answer Sabioc's question, this quantity here is what should be thought of as the central charge. At least in this Fock space. Yes, it should be gamma gamma prime. Thank you.
What is gamma gamma prime?
The product in cohomology. Yeah. Yes, yeah. So just like this pairing I wrote down took the product in cohomology and integrated up to some sign. Here we do the same thing, only we have this extra factor that we need to keep around. And this Euler class isn't anything too exotic. As an exercise, you can show in the language of the Frobenius algebras that Sasha introduced last week, this is what's assigned to this handle. Sorry? This is, so there was some correspondence last week between Frobenius algebras and 2D TQFTs. And so this surface here corresponded to some Frobenius algebra, which corresponds to some 2D TQFT. And under this correspondence, the Euler class of the surface corresponds to the element that's assigned by the TQFT to this element, to this handle. Okay. I'm supposed to use, all week I saw every speaker getting told to use the rag, and I was so looking forward to getting told to use the rag. Okay, so we have our Virasoro with central charge, and again, this cohomology of all my Hilbert schemas put together is a lowest weight representation. For this Virasoro. For this algebra generated by these Ln. So again, if I take Lm of gamma applied to 0, I get 0. No one objected to anything yet. So what happens when m is 0? So I apologize for not saying this earlier, but I should introduce these 0 modes, and that will introduce this U dependence I wanted to emphasize earlier. So I'm going to add a new generator, alpha 0, of gamma, and it will act on the vacuum and on everything acts by a scalar. And it'll depend on some parameter, say minus u times the integral of gamma. Okay. And so these formulas, sometimes m will be 0, and I need to say a 0 acts, and it's useful to make things depend on some parameter u. And that's how we can introduce this spectral parameter that showed up earlier. And so then, after I've added this in, I can say how L0 acts. And again, it'll act by a scalar. I've deviated slightly from my notes for the sake of time. So some of this, there may be some constant in front that I'm missing. But so for that, I apologize. But what I get is this. So here, so let me just, again, let me just call this u. This will be u squared. Apologize. And in the language of Virasoro algebra, this is what's called the conformal dimension. Including the integral. Not hugely important. And so the thing to note is that both this central charge and this conformal dimension are quadratic functions of this new parameter kappa I introduced. So maybe I'll keep this kappa around. Both are quadratic in kappa, are purely quadratic in kappa, or more precisely, they're invariant under exchanging kappa with minus kappa. And it's a fact that lowest weight representations of the Virasoro algebra, or a Virasoro algebra like this, will be classified by their central charge and their conformal dimension. And so I can give this VS the structure of a Virasoro representation in two different ways. I can have the Virasoro act by this, or I can have the Virasoro act, but every time I see a kappa, replace it by minus kappa. And the fact that both the central charge and conformal dimension are invariant under this change of kappa to minus kappa means that I'll get isomorphic representations. And so let me write down what I just said. This tells us that, in a better pen, this says that there exists an isomorphism sending, say, the product over I, sending some word in these Virasoro generators with kappa to the same word in these Virasoro generators equipped with minus kappa. And so this is some isomorphism of vector spaces over the field of all formal parameters I've introduced in the problem. So this is an isomorphism. Vector spaces, I guess, over the fields and this U and kappa.
You're not flipping lambda.
We're not flipping lambda. I just connected L with the minus sign. So let me call this operator suggestively maybe R1. Yeah. No, I mean so I think it should be, right? Because when you turn enough of the parameters off, it should become irreducible. And yeah. Yes. Yeah, so it should be irreducible. Starting from anything, I can get back to this vector. When I turn off when I turn off this parameter kappa, and so once I turn it on, that shouldn't create any problems. Yeah. Right. No, but they're irreducible in this case, which is important. Yeah. Yeah. So I mean, I guess in principle, this kappa could, I mean, in principle, it could be irreducible after you turn on kappa. My point was it's irreducible even before you turn on this kappa, and so it's going to remain irreducible after it's on. Right, but I'm just treating them as formal parameters. So I could pick up poles in these U and kappa, but. Sure, yeah.
Either way, I think you know what you want your isomorphism to be. Like, it's not just an abstract thing. Like, you have the exact same action on in both cases under this like minus kappa kappa, and you're just sending like you know the vacuum matches the vacuum, and then you just actify one guy or actify the same guy.
Right. I mean, it's some complicated rational function in U and kappa that you can write down explicitly. Okay, and so I'm maybe, yeah, so I think out of time. Okay, so let me say in 2 seconds how you pass from this R to the general R matrix. So to produce RU that acts in this tensor square, what I want to do is first write this tensor square in a different way. So what does typical generators here look like? Alpha M tensor 1 or 1 tensor alpha M. And I want to replace these generators by the subspaces generated by symmetric words in the Heisenberg and anti-symmetric words in the Heisenberg. And maybe I call this alpha M minus down here. And inspired yeah, I'm out of time, so maybe I won't explain this in full, but the kind of stable basis solution when S is equal to C2 guides you to the following answer. It tells you that R of U has to act by the identity in this first copy here, in this copy where everything comes with a plus. It has to commute with all of these operators. And it acts by R in the second factor. And so what does this mean? This is constructed by the same formulas as R1, only every time I see an alpha I replace it with this anti-symmetric version up to some scalar. Exactly. So in other words, I wrote these expressions in terms, these Virasoro generators in terms of these Heisenberg generators. And I produce new Virasoros that act just in this subspace by replacing this alpha m by this alpha m minus. And then it's a theorem that this R and so yeah, what is U here? So now I have, so if I had Vs of U, I have kind of two variables acting, right? I had a U acting on the first factor, maybe U1, and I have a U2 acting on the second factor of this Vs. And so here I have a U1 plus U2. Here I have U1 minus U2. And so this R of U is a function of U1 minus U2, and this satisfies the Yang-Baxter equation for any surface S.
Can you explain again how this R1 is related to that R?
Yeah, so it's just, so this R1 was written in terms of formulas involving these annihilation creation operators. And this R1 minus is written by the same formulas, only every time I see an alpha, I replace it by this expression here, and it only acts in half of the tensor product of this Vs. Okay, yeah, so I'm well over time, so I stopped there. I apologize for running over. Thanks. Yeah, sure. But again, I wanted to keep it, somewhat general.
Is there a chance you can make something like this work with appreciation?
I mean, in some way, one can do it kind of artificially. Like anytime, I would guess if you want torsion-free sheaves on some arbitrary surface, the Nigut has some stuff that's kind of similarly, not quite flavored in the same way, but in terms of constructing these quantum group actions on moduli spaces of sheaves. But I should also say one can kind of do this formally, stupidly here. Once you have some R matrix acting on a tensor square, the analog of cohomology of higher rank sheaves should be kind of tensor products, longer tensor products of this. And one can define the R matrix action by the same kind of fusion procedure that you would do for ordinary quantum groups. So this kind of doesn't see much of the geometry of the surface to begin with. So my guess would be you couldn't just apply this strategy to an arbitrary moduli space of torsion-free sheaves, but you can kind of do this algebraically. So really the only time we saw the geometry of the surface was in extracting its cohomology and looking at it as a Frobenius algebra. And that Frobenius algebra data was all we used to get this construction. And so I would guess that this version of this construction is too insensitive to see that. But. Yeah. Yeah. I mean, it's not clear to me, like, it's still, the fact that this construction works at all is still kind of surprising. Like, if you write down the stable basis and see how it intertwines with multiplication by this tautological bundle, the Virasoro formula kind of pops out. And my understanding is that this is really the technical basis for a lot of the connections between this gauge theory side and this conformal field theory side in Andre and Devesh's work. And I don't think that connection is kind of fully understood mathematically.
Was it for an arbitrary surface, not just a C2?
So in C2 is where you see this connection, but for an arbitrary surface you don't have this Nakajima side automatically. So but this still kind of works for an arbitrary surface.
How should I view this connection with gauge theory?
For an arbitrary surface, I don't know. Yeah. I mean, it's also not even clear to what extent surfaces are so important. So if I replace the cohomology of a surface by the cohomology of some higher dimensional variety, I can still make the same construction, but I don't know whether this theorem is true in general. So an answer either way would be interesting. But certainly for a surface, one can prove this. Yeah, sorry, I stopped there.